What is the ideal speed to take a 100-meter radius curve banked uh, at a 20-degree angle? Okay, so here's the top view of the road. So let's say you're driving in the circle, you're going like that. What you need is a centripetal force in this direction, or your centripetal acceleration is v squared by r. R is the radius of the circle. Okay, so now if the road were not banked, the centripetal force is provided by the static friction force, and so that'll it's static friction because your car is not moving in this direction, your car is moving in that direction. So the force is perpendicular to the direction of motion. So it's not moving in this direction, so that's a static friction force. Now, if the roads were flat, this static friction force, you would leave rubber on the road and your tires would wear faster. So again, this is a top view of the road. Okay, so now to prevent your tire from wearing out, what you do is you bank the road. Okay, so here's the bank and here's the bank angle. So here's your car again, and now here's the normal force that the road exerts. Okay, here's the weight of your car. So let me draw a cleaner diagram. So again, this is this part, so the banking is in this direction, the center of the circle is here somewhere. Okay, theta. So the normal force exerted by the road is in that direction, it's perpendicular to the road. Here's the weight of the car. Okay, so what is happening is, okay, so all right, let's see. Normal force. Okay, so this angle is 90 minus theta. This angle is 90 minus theta, and so is this angle. Those are opposite angles, 90 minus theta, and so this angle is theta. All right, now what's happening is this component of the normal force, this is Fn cosine theta, that is balancing the weight, and this component of the normal force, Fn sine theta, provides the centripetal force. Okay, so if you go at the right speed, and if that component of the normal force is enough to provide you the centripetal force, that's the right banking. And if you go faster than that, what you'll need is a static friction force in this direction that'll help you provide the centripetal force along with the normal force. So we'll assume you're going at the right speed where there's no static friction force. The idea is you don't want to leave any rubber on the road, and you want to make the static friction force 0. All right, so there's the theory behind all of it. So what you want is Fn cosine theta. So this component of the normal force is balancing the weight is equal to mg, and Fn sine theta, so we'll call this equation 1, 2, is providing the centripetal force. So Fn sine theta is mass times v squared by r. We'll call this 2. All right, so if you take 2 divided by 1, what you get is mv squared by r mg, and all this cancels, and what you get is tan theta. Okay, so tan of the bank angle is v squared by gr. Okay, so what all this means is, if the road is banked, so this road is banked at this angle, where tangent of the angle is the speed at which you're going, or this marked speed divided by gr. So if you go at this speed for a road that's banked at that angle, you won't need any static friction force. All the centripetal force will be provided by the normal force. So this component of the normal force will provide you the centripetal force. So this component will provide you the centripetal force. Okay. So of course, if you go faster than that at that bank angle, you'll need a static friction force. If you go slower than that, the static friction force is acting in this direction to prevent you from sliding. Anyway, so that's the relationship between the ideal speed and the bank angle. Okay. So let's add a page and do the numbers. Okay, so for our road, the radius is 100 meters and the bank angle is 20 degrees. So let's calculate the speed. All right, so tan theta is v squared by gr. V is square root of gr tan theta. Okay, so let's put in the numbers. 9.8 meters per second squared times 100 meters times tan of 20. Okay, and this works out to 18.9 meters per second. And 10 meters per second is roughly 25 meters per second, 25 miles an hour. So this is about 45 miles an hour. Okay, so the exit speed is 45 miles an hour for this ramp. Okay, that finishes this problem.